ended lesson 9, we're talking about work done by a spring. So we see that equation here. That was the very last slide that we covered in class. And we're going to go ahead and do an example problem with that. So here is our example problem. A force of 4.8 newtons is required to compress a spring and a projectile launcher by 15 centimeters. The launcher then shoots a 45-gram ball horizontally. We want to know what is the ball's speed as it leaves the launcher. That last little bit that we are assuming the spring is massless now is just to help make sure our math is not too complicated. So I've gone ahead and drawn a picture of what's going on. I have my ball inside my launcher. My spring is compressed. Right? That ball experiences weight. It's being pulled down by gravity. It is being supported by the launcher, giving it a normal force. We then see the fact that once we let go of that spring and let it expand again, that spring is then going to exert a force on our ball itself. When we look at the work done by the different forces on this particular ball, we need to look at how do those forces compare to the displacement. Our normal force and our weight are both perpendicular to our displacement, so the work in both of those cases is zero. So the work done by the normal force is zero, the work done by the weight is also zero. That is because the force is perpendicular to our displacement, and by definition when we do have those perpendicular, they do go to zero. So we do see the fact that the only force working on this particular object is our spring. So we're going to find out what is the work done by the spring. We already see we have the work spring formula. It is equal to the 1/2 our spring constant times our initial stretcher compression squared minus 1/2 our spring constant times our final stretcher compression squared. When the ball is leaving the launcher, our spring is actually going to be fully relaxed. It's going to be back to equilibrium. So the distance from equilibrium is actually going to be zero. That means that this final term then goes to zero. Our work done by the spring then becomes that. We are missing one particular variable out of this equation. We don't know the spring constant of our spring. It is a property of the spring, and we can find it given the other information that we have. We are given the amount of force required to stretch or compress that spring by a certain distance. That does tell us that we can use Hooke's law to find it. Hooke's law states that the force to stretch or compress a spring is proportional to the spring constant to the amount of stretch or compression. So our spring constant is going to be our force divided by our distance stretched. Our 4.8 newtons divided by our 1.15 meters. Please notice that I've gone ahead and switched from centimeters to meters. You do want everything in your base regular SI units. So meters, kilograms, newtons, seconds, that kind of thing. As a result, we do get the fact that K is 32 newtons per meter. That is the acceptable unit for our spring constant. Next, we are going to look at the fact that the work energy theorem says that the total work is equal to our change in kinetic energy. And the fact that our ball starts from rest goes ahead and tells us that our initial velocity is zero. This term goes away. Our work is done by the spring, so we are going to go ahead and set these two particular equations equal to each other. So our total work is equal to our work done by our spring. We do have 1/2 on both sides, so there's 1/2 to go away. And when we solve for VF, we do can simplify it just a little bit more since this xi is squared. It can be brought outside of it, and sorry, the xi is squared and is attached via multiplication, so we can technically bring it out. So we get this. We can now plug in all the information we know. We know that we stretch this 0.15 meters. We know our spring constant is at 32 newtons per meter. And we do know our mass of 45 grams does convert to 0.045 kilograms. And that does give us an overall speed of 4 meters per second. So this is what we would do to see what happens if our launcher is launched horizontally. How do you think this is going to change if we were to launch this vertically? Well, if we were to launch this vertically, we can no longer ignore weight. We do need to go ahead and take that into account at this point. So we're going to shoot it vertically. We have our ball in the launcher. It has the force from the spring, and it has weight of mg. The work done by the spring is actually not going to change. The work done by the spring is still going to remain this 1/2 kxi squared. What's going to change is the fact there is now work done by gravity. One thing I do want to note here is that we have not added normal force to our fixture. That is because we no longer need the support from the launcher itself. We are seeing all of our forces actually come from the weight and the spring. Right? So like I said before, the work done by the spring is going to remain the same. We are still seeing the fact that our work done by the spring is going to be in the force of our spring is still in the same direction as our displacement. But we are seeing something a little bit different when it comes to the work done by gravity. When we look at the work done by gravity, it is the force of gravity, or our weight. In this case, I've written it as mg. So the force done by gravity times our displacement times the cosine of the angle between them. My displacement is straight up, whereas my weight is straight down. So the angle between these two numbers is 180 degrees. So we do see the fact that our work done by gravity, this force is mg. Our cosine of 180 degrees gives us -1, and this whole term is negative. And then we have that displacement of our 15 centimeters we had before. So we have our work due to gravity is equal to our negative from our negative one that comes from our cosine of 180 degrees times our mg here. And then we're going to look at the fact that we have that change in position. We are seeing a initial position minus our final position to sort of mirror that relationship we see with the spring. Our final position is going to be at the relaxed position, so this is a displacement of 0. So our work done by gravity then is equal to negative mg xi. So our work total now is going to be made up of not just the work done by the spring, but now our work done by gravity. And remember that our work total is equal to our change in kinetic energy, 1/2 mvf squared minus 1/2 mvi squared. We are still starting from a rest position, so this particular term is 0. So we are then going to set this 1/2 mvf squared equal to our two equations for the work done by the spring. and the work done by gravity. So work done by the spring is our 1/2 mvf squared is equal to our 1/2 k xi squared plus our negative mg xi. I am going to go ahead and box over some of the algebra for this particular one, but we do see the fact that our final velocity is then equal to the square root of k over m xi squared minus 2g xi. We know our value for k. Our k is still our 32 newtons per meter. We know our amount of stretch of compression is our 0.15 meters. We do know that our ball is 0.045 kilograms. Gravity is 9.8 meters per second. So when we do plug everything into our calculator, we do get the fact that our ball